Good evening, guys.
Good evening, sir.
Good evening, sir.
So, what was the last topic we saw? So, yesterday we were doing some problems, right?
Yes, sir.
Okay.
Yes, sir.
Okay, I got it. Just a minute. Now we will start with the next topic. That is inductance. 1 minute. Sharing my screen. Now listen. Not sure why if I open one page, other is getting closed. Okay. So the next topic that we are going to see is inductance. Sharida. Okay, let me start it like this. Switch on my video. Sure. Yeah. So what are all the passive elements? You know what are passive elements, right? The elements which make use of the supply that we give. So what are all the passive elements that we have learned till now? There are in current electricity there was some passive element. What was it? You are mainly concentrating on one thing.
Magnetic flux.
The current electricity. I'm talking about passive elements. Elements are electrical components.
Soft iron core.
Current electricity resistors. Resistors are passive element because they cannot generate the power of their own. I hope you guys would have seen resistors. You need not see it also. You take a wire has a resistance associated with it. Correct? So I can call a wire though it is a conductor, it has some resistance. So I can call it as a mild resistor also. Correct? The carbon resistor, or the wired resistor, or whatever it is. Right? So resistor is a device which has an important property associated with it. What is it called as? It's called as resistance. Similarly, we saw another passive element which is called as a capacitor. Anything that ends with OR is a device. Right? And anything that ends with A and CE is a property. Correct? So a capacitor is a device which has a property associated with it called as capacitance. Like for example, this water bottle is there. This water bottle has a capacitance associated with it. What is it? It depends on how much volume of water it is able to hold. That is the capacitance. That is the capacity of this. Right? In a similar way, a capacitor is a device which can hold a certain amount of charge in it. Now the topic that we are going to see is inductance. So what do you think is inductance?
The property to induce something.
So something related to induce. So inductance is definitely a property because it's ending with A and C. That is according to the, I'll call it as nomenclature or grammar of physics, whatever it is. Okay, according to the grammar of physics, anything I understand that A and C that ends is what is called as a property. Then what device do you think will have a property associated with it called as inductance?
Inductor.
Inductor, right? So that is what we are going to learn now. So first we are going to see the property called as inductance, and then we will see the property called as self-inductance and mutual inductance. And all these things are going to happen for a device called as inductor. Sariyada? Before that, before we try, I'm just trying to ask certain questions so that we'll understand things better. So when I say inducing something, see, one thing I'm clear from the beginning of this chapter. What is the name of this chapter? Electromagnetic induction, etc. Okay. So this electromagnetic induction is that kind of a phenomenon which will get introduced under what context? What is the necessary thing that is supposed to happen for you to have an EMF induced in the circuit?
Magnetism.
Sorry, da?
Magnetism.
Okay, magnetism is there. What should happen to that magnetism?
It should get induced.
Magnetism is not induced. Electromagnetic induction, magnetism induced. Think about it.
Movement of
Is it magnet?
electrons.
Movement of electrons.
It is the EMF that is getting induced.
Okay.
It is the EMF that is getting induced due to some preliminary changes you bring in the case of magnetism. What are you doing? What is the necessary thing? What did Faraday say? What did Faraday say? He
And
told
there is
that
a relative motion between the pickup coil and the magnet. Current EMF is induced.
EMF is induced. Yes. What is happening? What is technically, see, relative motion is a physical phenomenon that you're able to see. Right? I have a coil in my hand, I have a magnet, I am able to move it. Yes, that is a physical movement that you're able to see. But by that kind of a motion happening, what in terms of magnetism is changing? I want that word. I'm just trying to pull that from your mouth. I told this already. What is changing now? By you bringing the magnet close or taking it away, what are you changing within this pickup coil?
Magnetic flux.
Motion of electrons.
Magnetic flux, magnetic flux.
Okay.
By changing the magnetic flux, you are able to put the electrons into motion. Correct?
Okay.
Right. So the basic, like how I tell every time, like if you see the 4th chapter and 5th chapter, it was all about magnetism only. And if you see the preliminary idea behind magnetism, what comes to your mind? If anybody asks you, sir, what they come and ask you, how is magnetism generated? What is the reason for magnetism to get induced in a material or to exist in a material? What will you say?
Movement of electrons.
Movement
It is
of
a flow of
charges.
charges.
Electrons.
Flow of charges, right? So it need not be electrons always. It can be ions also, like how we talk about Earth's magnetism when we talk about ionization around the Earth's surface, right? So it is a motion of charges that is important for you to have magnetism present. In a similar context, if somebody asks you a question, what is a preliminary thing to happen for you to generate EMF from magnetism? The answer is change of flux. It's the only thing, nothing else. So when I talk about inductance also, I am trying to talk about the EMF that is getting induced across the ends of a inductor. If there is a device called as an inductor, then I'm interested to study about what is going to be the EMF that will get generated across the ends of that inductor. For that to happen, what am I supposed to ensure?
Magnetic flux.
I need to ensure that my magnetic flux is changing continuously with respect to time for me to have a non-zero EMF.
Yes.
The moment the change of EMF is going, the moment the change of flux is going to stop, EMF is going to die. Right? That's what the reality is, right? That's what the chapter is basically telling us. Correct? So now we will try to understand what exactly inductance means, and we will try to give a mathematical expression to it, along with some derivation for the self-inductance of a solenoid and the mutual inductance of two circular coils. That is what today's topic of discussions are going to be. So shall we get started? Please. Inductance. Write down the heading as inductance. Generally, the symbol used for inductance is capital L. Okay, this inductance is sometimes called as self-inductance also. We will see what it means. Now see, an electric current, right? An electric current can be induced in a coil by flux change produced by another coil in its vicinity, or flux change produced by the same coil. So what should happen is, see, I have a coil. I have a coil in my hand, and if there is a constant current flowing through this coil, right? If this is a circular coil, we know how the magnetic field lines are due to a circular coil. From your 10th standard basics also, you would have learned. So they're going to be something like this, right? I hope you guys are able to visualize this, right? Little bad diagram, but bear with it. Yeah. So this is how the magnetic field lines are going to be. Now my question is the value of magnetic field at any point on these lines going to be a constant or a variable? Are you able to understand what I'm asking?
Can you repeat the question, sir?
Yeah. If I take any point on this magnetic field lines, is the intensity of magnetic field, that is B, going to have a constant value or a variable value? Don't think only in terms of this chapter, okay? Think using your logic. Sometimes my question will be related to 4th chapter also. So I have a steady state current flowing in this coil. Concentrate on the word I'm using. I have a steady state current flowing in this coil, due to which I have magnetic field lines piercing through this coil itself. My interest of study is I want to know whether these magnetic field lines are going to be a constant or a variable. So to answer that, you need to recollect and think, who is responsible for these magnetic field lines?
Electrons.
No, which electrons? Electrons, where are they flowing actually?
The coil.
Through the coil, right? And what did I say the coil has? The coil has current, and what is the nature of that current? It's a
Steady.
Steady state.
What do I mean by steady state current? Means it's going to have a fixed value. When it is going to have a fixed value, then the amount of flux, amount of magnetic field that is going to pass through this, isn't it going to be a constant?
Yes, sir. It will be a constant.
It's a constant, right? So in this case, is it possible for me to induce EMF?
No, sir. It has to keep changing. The
It
flux
has
should
to keep changing, right? That is what we have been discussing from the beginning. So if I need to ensure that it has to change, then I need to ensure that my current is changing. That makes sense? Correct? So what I'm trying to say is, I can change the flux that is linked with this coil. I'm saying that the flux that is linked, the magnetic flux linked with this coil, isn't it directly proportional to the amount of current that is flowing there? Because if I increase the value of current, the value of magnetic field will increase.
Yes, sir.
If the amount
sir.
of magnetic field is increasing, isn't there a change in flux going to happen? Similarly, the vice versa is also going to happen. If I decrease the value of current, B will decrease and flux will also decrease. So I can blindly conclude that the amount of magnetic flux linked with this coil is directly proportional to the amount of current that I'm passing through this coil. As simple as that. But if I am able to make, now listen to this carefully and tell me logically, if I am able to make this current change with respect to time, will I be able to change the flux also with respect to time?
Yes, sir.
Yes, sir.
Correct. So from this, if I expand and write, can I write that the change in magnetic flux with respect to time is directly proportional to the rate of change of current? Can I write it like this? Isn't it directly proportional to dI by dt?
Yes, sir.
Right? So that is what the statement they are given here. So the flux through a coil is directly proportional to the current. Further, if the geometry of the coil does not vary with time, what do we mean by geometry? I'm talking about the area and the orientation. If these two parameters are unchanged with respect to time, then I can blindly conclude that the rate of change of flux is directly proportional to the rate of change of current. Okay, are you guys able to understand this statement, mathematical statement?
Yes,
Now,
sir.
our job is to define what this magnetic inductance means. Now, listen to this carefully. I'm revisiting the statement again. Now, I'm going to define inductance. Flux linked with the coil is directly proportional to the current. If I multiply this value with N, then it means that the coil has N number of turns. So N times the flux included for each coil, isn't it directly proportional to the amount of current flowing through the circuit? So from this, can I conclude one thing? That N times phi B should be equal to some constant times I, correct? And the constant that you're going to introduce is what is called as inductance. Okay. So that is the meaning of the statement. N phi B is directly proportional to I. The constant of proportionality in this relation is called as inductance. Okay.
Sir, one doubt, sir.
Please say it.
Sir, N phi B equals Li, no, sir. So if we take N to the denominator, will the flux be inversely proportional to the number of turns?
No. That is not happening. Whether you talk about the flux through one coil, okay, whether you talk about the flux through one turn or whether you talk about the flux through N turns, it depends only on the magnitude of the amount of current. It is not like N phi B is directly proportional to Ni. I didn't say that.
Yes, sir.
If you pass 5 amperes of current through one turn or N turns, then N times that flux is directly proportional to that 5 ampere only. That is the meaning.
Okay.
So you should not take the N to the other side.
Okay.
Okay, because why I am saying this, flux is dependent only on the current. What you are asking, no? You know what is the meaning of it? Phi B is directly proportional. You are saying something like this. So you are
Yes,
trying
sir.
to say flux will decrease if the number of turns are increasing.
Yes.
That is not the case because flux is not dependent on the number of turns. Rather, it is dependent on the amount of current that it is flowing.
Okay.
Okay. So, but that's a good question. So the answer is this thing. I hope you understood. So this L is called as inductance. Seriada. So the constant of proportionality in this relation is called as inductance. And there are certain important properties to be associated. See, these are all 1 mark questions. Please make a note of it. We will see it in the future, okay, that inductance depends on the geometry of the coil and some intrinsic material properties like permeability of that material and all those things. That we'll be seeing, okay. So is it not something similar to capacitance? You remember C is equal to epsilon naught A divided by D. And there is a formula C is equal to QE. I asked you a question at that point. If I increase the value of Q, can I increase the capacitance? Can I do that? The answer is no. Because the capacitance does not depend on the electrical properties of the material or like electrical properties like charge or potential difference. Rather, it depends on the geometrical parameters like A and the distance of area of cross section and the distance of separation along with the permittivity of free space. That is what you need to understand. Am I clear?
Yes, sir.
Okay.
Yes.
So please make a note. N into phi B is equal to Li, right? So L will be equal to N into phi B divided by I. So this is one of the mathematical expressions of whom? Of inductance. So this is one of the formula. Remember this, okay? We'll be using it in the future derivations. So at that point, you should understand. Okay. Now, similarly, if I extend this, N phi B is equal to L into I. If I differentiate on both the sides, N into d phi B with respect to dt is equal to L into di by dt. Okay. Then what do I call this, guys? according to the Faraday's law of electromagnetic induction, what does N into d phi by dt represent? You have solved problems also. Refer your notes and tell me.
That's the EMF, right?
It is the EMF. Okay. Actually, to be more specific, it is negative of the EMF. Because minus sign is the significance of Lenz's law, no? Minus E is equal to L into di by dt. So EMF will be equal to minus L into di by dt. Are you able to understand, guys?
Yes.
So what will L be equal to? See, unfortunately, I don't know why my software is not supporting to open two documents. That is why I'm writing everything on the same page. Okay. If I open the other page, this will get closed. So please bear with me for today. So L is equal to magnitude of EMF divided by di by dt. This is another mathematical definition for whom? For inductance. So basically, there are two mathematical definitions for inductance. What is it? One is N phi divided by I. Correct? There's one. And the second mathematical expression is magnitude of EMF divided by the rate of change of current. Clear, guys?
Yes.
Right. So can I erase this?
Yes, sir.
Now the question is, what is going to be the SI unit of it? So if I observe the SI unit of it, N into phi b divided by N regular. SI unit, what will it be? The SI unit of flux is, see, for N there is no unit. Weber per ampere. Or I can write Tesla meter square per ampere, both are right. Because 1 Weber is Tesla meter square. Flux is equal to B into A. So this Tesla meter square per ampere is what we can call it as HENRY, which is also called as Henry. Okay. So the SI unit of inductance is Henry, and it is represented by the symbol capital H because it is named after the scientist Joseph Henry. Okay. So have this in your mind. Like, see, there was, what is the unit of capacitance, guys? Is it not Farad? So capital F, right? But if you see, the capacitance is never written in terms of Farad because Farad is a very big quantity. If you go revisit all the questions and see, they'll generally be in terms of microfarad, right? Because of the size of the capacitor that we have in real-time applications, the capacitance is generally written in terms of microvalues. In a similar way, you will not have inductance in terms of Henry, rather you will have the inductance in terms of milli. Most of the questions you will have millihenry. So generally for capacitance will represent micro, and for inductance will represent in terms of milli. Sharia. Right? Now our job is to derive the self-inductance of a solenoid. So first we will derive self-inductance, then we will go to mutual inductance. Okay. So we will see self-inductance. Self-inductance is represented by the symbol L. Okay, that is why I told you inductance and self-inductance, they have the same meaning. Okay. Now what we are going to see is self-inductance of a solenoid. Okay, we'll see the self-inductance of a solenoid. Please write down the heading. Okay. So before that, we have already seen this N times phi b is directly proportional to I, N phi b is equal to L times I, all those things. And this also I showed you, EMF is equal to minus D into N phi b divided by dt. So EMF will be equal to minus L into di by dt. Correct? So having all these things in mind, we will see what is the meaning of self-inductance. But before we see self-inductance, first we need to understand what it actually means. So listen. If I have a solenoid, okay, if I have a solenoid which is controlled with the help of a battery and a switch. Now, initially, what is the amount of current linked with this coil?
What did you say?
When the switch is open, the amount of current linked with the coil is zero. When the amount of current linked with the coil is zero, can I say magnetic field is zero? When magnetic field is zero, can I say that the flux is zero? They're interlinked. Now, as soon as I close the switch, what will happen? When the switch is closed, see, there is a concept called as growth of current. Means, let's say the current in this coil is flowing at a rate of, let's say 2 amperes per second, 2 amperes. Okay. Now the question is, initially when the switch was open, it had 0 ampere. There was no current flowing. But as soon as the switch was closed, it went to 2 ampere, right? But there will be a time gap between 0 to 2 ampere where the current is growing. That phase is called as the growth phase of current. Are you guys able to understand what I'm trying to say? So before the switch is closed, it will not immediately reach 2 ampere. It will slowly go from 0 to 2 ampere. Let's say there is one particular instant where the current is 0.5 ampere. So let's say this is happening in few seconds, few microseconds also you can take it. Okay. When it is going to happen in this amount of time, when the current is going from 0 to 0.5 ampere, let's say in 0.01 seconds. Okay. Just random numbers. So between the time t is equal to 0 and 0.01 seconds, can I say that there is an increase in the value of current? As a result of which, there will be an increase in the value of D. As a result of which, there will be an increase in the value of flux. So what has happened? Initially, the flux was 0, but in 0.01 seconds, at that instant, what I can say is the flux has got increased. And from the basics of solenoid, we know that the magnetic field inside the solenoid is going to be in this way, and its value is given as mu naught times N into I. Guys, do you remember this? We derived it using Ampere's circuit law.
Yes, sir.
So the value of magnetic flux linked with the coil is mu naught times N into I, and can I say that the amount of flux linked with the coil is going to change between these two values, as a result of which, if change of flux is taking place within the solenoid for that 0.01 seconds, what is that you're going to expect? What can you expect?
Change in magnetic flux.
When there is a change of magnetic flux with respect to time, what will happen?
Inductance.
Magnetism is induced.
EMF is induced. Correct? So there will be, means apart from the already existing voltage, there will be a voltage which will get generated at the ends of this conductor or at the ends of this solenoid. And that EMF is generally called as back EMF or self-induced EMF. And this phenomenon of generating EMF at the ends of the coil due to its own current is what is called as self-induction. So there are three words that we are going to see. One is induction, one is inductor, and the second is inductance. What do we mean by induction? Induction
The
is
process by which inductance,
yes,
like something is
process
induced.
by which we induce EMF across the ends of the conductor due to its own current.
Yes.
Because it's happening on its own, that is the reason why we call it a self. Sharia?
Yes.
Okay. And the inductance that this coil possesses is what is called a self-inductance. Since it is able to induce EMF at the ends, then the solenoid also behaves like an inductor. Okay, there is no separate, like how you call a copper wire also as a resistor, like you can say the solenoid is an inductor. I will explain what is an inductor clearly in the next class. But as of now, tell me, are you guys able to visualize the process that is happening here? Did you understand the sequence?
Yes, sir.
Right? Now, our job is to find what will be the self-inductance associated with this solenoid when this kind of a phenomenon takes place. Okay, that is why the heading is said to be self-inductance of a solenoid. Shariyada. So write it down. So it is possible to calculate the self-inductance for circuit with simple geometries. Okay, let us calculate the self-inductance of a long solenoid of cross-sectional area A and length L, which is also having the number of turns per unit length as small n. Then I told you one thing, right? We know that N phi B is equal to L ida. What is our job? What are we trying to find? We are trying to find self-inductance of the solenoid. So what is the formula for self-inductance? N times phi B divided by I.
Yes.
So I'm just explaining the steps, the algorithm to solve these kind of problems. How to remember the derivations of them. So since I need to find the self-inductance, what I'm trying to do is I will calculate the flux that is associated with the coil and divide it with the steady state current. I repeat, I'll calculate the flux that is associated with this coil and divide it with the current. So what is the flux that is associated with this coil? Let's say it has capital N number of turns. Capital N times phi B is equal to, can I write it as capital N into, what is the amount of, what is the formula for flux basically? B into A into cos theta, where theta is going to be the angle between whom? Magnetic field and the area vector. So capital N is capital N only. I'm not disturbing it. What is the value of B? Mu naught times Ni. And the area of this coil is generally pi r square. As of now, I will write it as A only. Because the cross-sectional area, when you see it from the left-hand side or right-hand side, that curvature will look like a circle. A into cos of 0 degrees. Correct, Ada? So this is the value of N phi B. Then inductance is equal to N phi B divided by I. Means I need to divide this whole expression with I. When I do that, what am I going to get? Mu naught small n into capital N into A. That's it. That's all with the derivation. Okay. Mu naught small n into capital into A is going to be the inductance of this, but we'll do some small manipulations. That's it. So this will be equal to mu naught into small n into, what is the value of capital N? Capital N, is it not equal to small n into L? Where small n is the number of turns per unit length, then L stands for the length of the solenoid multiplied with the area. So mu naught n square A into L is what is the self-inductance of a solenoid. That is why if you see in the beginning of this inductance, we would have told what? It depends on the geometrical parameters and the intrinsic properties of the material. Seriya?
Yes, sir.
Am I clear? It is only 3 steps. Just write it down. Done? Suppose instead of we having an air medium, had there been a soft iron core whose permeability is mu, then we can write L is equal to mu into n square Al. But we know that mu can be written as mu r into mu naught and n square into A into L. Clear? Now see, the self-induced EMF is also called as back EMF, as it opposes any change in the current in the circuit. Okay. So basically, if you have to speak about the self-inductance plays the similar role like inertia. Okay. So have this point in your mind. Okay. Now, I'm going to explain you the significance of inductor. So this is one of the points which many people fail to understand. If you go and ask them, they don't know what is the significance of inductor. Now listen. See, if I ask you what does a resistor do, what will you say?
So anything that resists the flow of current.
So resistor is a device which opposes the flow of current. Okay. So that is from the definition. Will you be able to analyze the same thing using a mathematical expression? Let's try to have a different perspective. Okay. So what I'm going to do is I'm going to understand the mathematical relation between resistance and current. I know that V is equal to IR, then I will be equal to V. Sorry. Then R will be equal to V divided by I. I can write V, or sometimes I can write it as EMF also, provided it's a circuit with, it's a cell with zero internal resistance. Now, I wrote E for a reason, you'll understand it. Now, can I say that resistance is inversely proportional to current? Correct.
Yes, sir.
So, if I keep the EMF fixed, I'm able to understand that resistance and current are inversely proportional to each other. That is why I'm trying to say that resistor is a device which opposes the flow of current. Right? Because of the inverse operation in terms of mathematics. Now, I have another question. When I say E is equal to L into di by dt in terms of magnitude, then L will be equal to what? E divided by di by dt. Correct, Adam?
Yes, sir.
Okay. So listen to this very carefully. Resistance is a property which opposes the flow of current. Right? Resistance is the property which opposes the flow of current, and inductance is a property. Look at the expression and tell me which will oppose what? What is inductance inversely proportional to?
Change in current with time.
It is inversely proportional to L into di by dt. Means if somebody asks you what an inductor does, you know what people say, inductor will induce EMF. No, it's not that simple. Inductor is a device which will oppose the rate of flow of current or rate of change of current. Please write it down. Nowhere in the book you will find it. Huh? Please write it down. Later you might not understand it. So inductor is a device which opposes whom? Which opposes the rate
of flow
of
of current.
no, not flow, rate of change of current. Sorry, if I had told rate of flow, please correct it. It opposes the rate of change of current. Means inductor will not like current to change with respect to time. It wants only constant current to flow through it. Are you able to understand? Like how a resistor always wants less amount of current to flow through it. An inductor will only want a constant current to flow through it. It will not like when current keeps changing with respect to time. Okay.
Okay, sir.
And this is the reason why, please write it down. And this is the reason why inductor offers a very high resistance. This is the reason why an inductor offers. This is the reason why inductor offers a very high resistance to alternating currents. So if you see, an inductor will provide more amount of I can call it as resistance also, more amount of opposition to the alternating current. It will allow DC current to flow through it smoothly, but it not allow the alternating current to flow through it. It is because of this reason. Okay. And the symbol used for inductor is something like this. And the symbol used for inductor is something like this. Don't mistake it as a solenoid. It is not a solenoid. That is a symbol used.
Sir, is it just a solenoid or a solenoid with a bar in the bottom?
No, nothing. It is not a solenoid. That's what I'm saying. Don't mistake it with solenoid. Don't get confused with solenoid. This is an inductor. No bar. There's no bar. Sorry. This is an inductor. Okay. So based on this, we are going to calculate how the so-called inductor will be able to store energy in it. How will inductor be able to store energy in it is what we are going to see. Like if I ask you about a capacitor, so what does a capacitor do? Capacitor will store the energy in it in the form of electrostatic field or electric field. In a similar way, inductor will store the energy in it in the form of magnetic field. So how is it going to do it? That's what we are going to see. So please write down energy stored in an inductor. Okay. Shall I proceed? So we know the formula for power, electrical power, as magnitude of EMF into current. Right. But how is power basically defined as? Power is basically defined as the rate of doing work. Right. But how is EMF defined as? EMF is defined as L into di divided by dt, and here you have an I multiplied dw by dt. Okay. Then I can conclude the dw is equal to L into I into di. So dt will get cancelled, L into di, I into di. So integral. Here I have to integrate with respect to I. Here I will integrate with respect to work done. 0, 0, I, W. So integral of W between 0 to W is W. L is a constant, will come out. L into integral of IDI is I square by 2. So half L I square divided by 2 is the amount of energy that will get stored in whom? The amount of energy that will get stored in the inductor in the form of magnetic field. Done? Do you guys finish it?
Yes, sir.
Now, sir. Now we'll go to the next concept of mutual induction. Okay. The next concept that we are going to discuss is mutual induction. Then we'll discuss mutual inductance. Okay. Listen. So in self-inductance, what is happening? There is an EMF generated across the ends of that solenoid due to its own current change. Whereas if I have a device like this, where this is one device, this is an other device. Okay. Now listen. One device is connected to a potential source. The other device is connected to a galvanometer. Now, when I close the switch, see initially when the switch is open, what can I say about the current through this? Obviously, current is zero, flux is magnetic field is zero, flux is zero. Since there is no magnetic field, that will not be associated with this coil also. Now, when the switch is closed, okay, when the switch is closed, what will happen? The current in this will increase. Due to the increase in current, there will be a magnetic field through this. And this magnetic field that is getting generated will also get linked with the second coil. Are you able to understand? First, second. So initially the flux that was linked with the second coil was zero. Whereas in this scenario, what has happened? Since the value of current is increasing the first coil, the current is generating a magnetic field as a result of which magnetic flux, and that magnetic flux is getting associated with the coil number 2. I repeat, it is associated with the coil number 2, and that value, and that change in flux is what is going to create an EMF, and you can see that the galvanometer will show some deflection. So this kind of a phenomenon where flux is generated by current is passed through one coil and EMF is generated in the other coil is what is called as mutual induction. What is it called? It's called as mutual induction because change of current is taking place in one coil and EMF is induced in the other coil. It is a mutual relation. So that's why it's called as mutual inductance. Am I clear, guys? So in mutual inductance, you will have two devices where one is called as primary and the second one is called as secondary. So what do you mean by a primary device? Primary device is the one which is connected to the battery source. Secondary device is the one in which EMF is induced. Okay. Guys, am I clear or not?
Yes, sir.
Yes, sir.
Right. Now we need to understand what mutual inductance means. Right. It is slightly tricky one. Observe this. Now what is happening is, can I say that the flux linked with the second coil, number of turns in the second coil multiplied with the flux through each coil, each turn, is directly proportional to the current in the first coil, because the flux in the second coil is getting linked because of the current in the first coil, unlike the previous situation. The previous situation, what happened? The current and flux were linked within the same coil. That is why it was self-induction. Whereas here, the flux in the second coil is linked because of the current in the first coil. Right? Then, if you remove the proportionality symbol, N2 phi 2 should be equal to something into I1, and that something is nothing but M21. That is a mutual inductance. So M stands for mutual inductance. It is a mutual inductance of the second coil with respect to first coil. Am I clear, guys?
Yes,
Yes,
sir.
sir.
Okay. Then how do you write M2N as? M21 will be equal to N2 phi 2 divided by I1. Remember it like this. 2, first number, numerator will have 2. Second number will be present in the denominator. In a similar way, if I have to write the vice versa, then M12 will be equal to how much? N1 phi 1 divided by I2. Guys, tell me, is this concept tough? Are you able to understand? Yes or no?
Yes, sir.
Right. Now, what we will do is, our job is to, so in the previous case, what we did, we derived the self-inductance of a solenoid. Now we will derive the mutual inductance of two solenoids. And here an important thing is, we will be considering two solenoids of the same length L. I repeat, we consider two solenoids of the same length L, and one is of the radius of cross section R1 and the other is of the radius of cross section R2. Okay, well. So the inner one is called as S1 and the outer one is called as the S2. So S1 has N1 turns and S2 has N2 turns. Any doubt till here? And this kind of an arrangement is called as coaxial. Co means same, axial means axis. Say they both share the same axis, where this line is called as the axis. Okay. Now listen, guys. Now, our job is to derive M21 and M12. Let's see how to do it. Now, so I want you guys to answer it so that you'll understand it better. Now listen. Okay. So, if S1 is primary, and S2 is secondary. So what do you mean by primary? Primary is the one which is connected to the
Battery.
battery. So in the first scenario, since we have two coils, it is up to us which one you want to make it primary and which one you want to make it secondary. Okay. So in the first scenario, I'm making S1 as primary and S2 as secondary. Now answer this question, guys. Now, can I say that the flux linked with the secondary coil N2 into phi 2, is it not directly proportional to the amount of current that is flowing through the primary coil?
Yes, sir.
So N2 phi 2 will be equal to how much? Is it not M21 times I1?
I1.
I1. So M21 is how much? N2 phi 2 divided by I1.
I1.
Correct, Ada? Now the challenging part is what is the value of phi 2? So M21 is equal to N2 is undisturbed. What is phi 2? That is a flux linked with that is a magnetic field linked with the second coil, area of the second coil into cos 0 degrees, the whole divided by I1. Did you understand what I did? So phi, basically phi formula is dA cos 0. I don't want anybody to write this step. I'm going to do a small correction. Okay, I wrote it because this is a mistake many people do. Don't write it, wait. See, I can write the magnetic field of the second coil only when it has generated the magnetic field. But here, who's generating the magnetic field? The magnetic field is generated by the conductor which is connected to the battery source. Who's connected?
S1.
One. Correct? So here it is B1. First important point to be noted. So I hope you understood what is the mistake that happens. Don't write it as B2, A2, your answer will be wrong. Secondly, the magnetic field within a solenoid is generated inside it. We know this fact. So magnetic field due to a solenoid is generated within it. When that is the case, then the maximum flux that can link with B2 is nothing but the flux through this coil itself. So whatever is the flux that is linked with the first coil, the same flux will be linked with the second coil also. Logically, that's the meaning, right? So here you should not write A2, you should write it as A1. So though it is the flux linked with the second coil, but since the first coil is completely present inside the second coil, the flux linked with the second coil is exactly the same that is linked with the first coil. Okay, so this will be equal to N2. What is the value of B1? Is it not mu naught times N1 into I1 into A1 is undisturbed, cos 0 is 1, the whole divided by I1. I1 and I1 will get cancelled. This will be mu naught N2 N1 into A1, but N2 is nothing but N2 in small n2 into L. So mu naught N1 N2 A1 into L. But here, okay, there's the value. Am I clear with this? So the magnetic inductance of the second coil with respect to 1 is equal to mu naught N1 into A1 into L.
Sir, one doubt, sir.
Hmm.
Sir, won't the flux decrease with distance?
Why? No, in this case, the second coil and first coil, first coil is completely within second coil. Why would it decrease with distance?
Okay.
So whatever is the flux that is linked with the first coil is the same flux present within the second coil.
Second coil. Okay, sir.
Yeah. See, it is like this for you to understand. Let's say I have two coaxial cylinders here. I have one cylinder, and inside I have another cylinder. If I take the charge inside the smaller cylinder as, let's say 5 coulomb. Now I ask you a question. What is the total charge enclosed by the bigger cylinder? What will you say?
5 coulomb.
It is 5 coulomb because whatever is the charge the smaller cylinder is holding will be the same charge around the bigger cylinder also.
Yes, sir.
Because the bigger cylinder doesn't have any charge of its own. Same is the case here.
Okay, sir.
Got it? Now see. The second one is even more tricky. Now see. We did for M21. Now it is M12. Okay. Can I rub this portion?
Yes, sir.
Now see. Now I'm making S2 as primary and S1 as secondary. I want everybody to be very careful. Okay. Now, what will happen? The flux linked with the secondary coil, that is N151, is directly proportional to I2. So I will get M12 is equal to N151 divided by I2. I have already told this, right? I'm sure if you would have written it also. So we derived M21 in the previous case. Now it is M12. M12 is equal to number of turns in the first coil into what is the value of phi 1? BA into cos 0 degrees, the whole divided by I2. This is where you need to be careful. Now, who is acting as the second primary coil? S2. So means S2 is connected to the power source. So the magnetic field is generated due to the second coil. Correct? So there is going to be magnetic flux throughout. Sorry, magnetic field throughout. Throughout whom? Throughout the bigger coil. But when I say phi 1, what do I mean by phi 1? Guys, I need an answer. What do I mean by phi 1? Phi 1 is the flux linked with the
S1.
S1, right? So from B2, can I say only this portion of B2, right? B2 is passing only through this portion for the flux through the first coil. So here the tricky part is, though the magnetic field is generated due to the second coil, but the flux linked with the first coil is still going to be only within its area. So in the previous case, what was it? It was B1A1. Now it is B2A1. Okay. So it will be N1 into what is B2? Mu naught into N2 into I2 multiplied with A1, the whole divided by I2. This and this will get cancelled. And this will be mu naught N2 into capital N1 is nothing but N1 into L into A1, the whole. That's it. Now, can you guys tell me what is the value of M21 that we derived? It would have also been mu naught N1 N2 L into A1. Correct?
Yes, sir.
So, if you observe in this case, if you take two solenoids and place them coaxially, also if they satisfy the condition that they have the same amount of length, then the mutual inductance of the first coil with respect to the second is going to have exactly the same magnitude as that of the second with respect to one. They both are going to have the same value. Please make a note of this point. Provided what condition is satisfied? They both are of same length. So that M21 is equal to M12 can be called as capital M. And you need to remember this expression because questions are asked based on this. So sometimes what we do is instead of A1, you write it as pi R1 square. That is what the expression they have given you. So you can make a note of that point also. Clear, guys?
Yes.
Okay. So this is all about inductance, self-inductance, and mutual inductance. So these are all very important derivations, and you have applications of them as well. So please ensure you practice it again. Okay. So next class we'll be discussing about eddy currents and AC generator, and then we are done with this chapter. Okay. It's a small chapter actually. That's it, guys. So any other doubts from today's class?
No, sir.
So,
That's good. Okay, then we can wind up. This can be.
Thank you, sir.
thank you,
Thank you,
sir.
sir.
Thank you.